Okay. Hello everyone. My name is Donghui Chen. I'm an OpenAI iTunes segmentainer. Today I want to share you with you the iTunes, which is an AI-based automatic parameter tuning system. I will introduce iTunes from the following four aspects. First, I want to introduce what is the performance tuning. This is a simple example for a metric multiplication of 4,800 by 4,800. If we write it in Python language, it will take more than 60,000 seconds to run. However, if we use C language to write it, it only takes about 600 seconds to run. Then, if we optimize by multi-thread parallel computing, then we can only take about 47 seconds. Then, if we use other optimization algorithms, such as the vector instructions, it only needs to take 1.99 seconds. This simple example gives me we can say that there are huge room to improve our performance. Then I will give an instruction about the iTunes. As we can see, an operating system have a mass number of parameters and complicated correlations between links. However, those tunable parameters control all aspects of the operating system. For example, in Spark, there are so many tunable values. If we use the default values, they can't get the best performance. Then we want to tune these parameters. For example, there are several advantages. For example, the execution time of Spark can drop 10 times, and the system resource utilization could up to 10 times, and we can also reduce some errors, such as the OM and timeout, and so on. However, tuning parameters have several challenges. The first one is that there are many parameters in a single system. For example, in Spark, there are more than 200 parameters. Then the second one is that there are a huge number of systems. For example, there are so many applications, such as the vertical applications, analytics, and visualization systems. Different systems need different kinds of parameters. Then the second one is that there are diverse workloads and system complexity. For example, even we use the Spark, there are all kinds of workloads. For example, there are including the MLlab streaming cycle and the graph processing and so on. Different workloads also need a different kind of parameters. However, if we using manual tuning to tune these parameters, there are several disadvantages. For example, it requires long tuning time and requires individual appearance and has high labor costs. However, if we use AI to automatically tuning, there are several advantages. For example, it only needs short tuning time, and there is no need for individual appearance, and it only needs matching costs. Therefore, the object of iTunes is that given a workload, we want to use AI to find the optimal parameters for a given workload and achieve the best performance. Now, let's see the related works. As we can see, tuning is a constant topic. In the 1980s, there are manual tuning have been used. In 2000s, statistical and heuristical methods are widely used. Recently, in and turns, traditional machine learning methods are also widely used. Recently, deep learning and reinforcement learning methods are also widely used. The following table gives the performance of all the road methods under the several dimensions, such as the quality, efficiency, and to deal with the three challenges. As we can see, there is no single kind of method performed best under all the dimensions. Now, we want to use AI to perform the automatic tuning. There are several advantages. For the first one is the full stack coverage. We can leverage a variety of technologies to optimize several layers. The second advantage is the intelligent exploration. We can explore tuning opportunities in an efficient and intelligent manner. The third one is the target orientation. We can tune the system based on objects and constraints. The third one is the full automation. We can conduct the entire tuning procedure automatically. Then we design a tune, which is an AI. We use AI to enable the optimal performance of the system. First, we need to collect all kinds of data, such as the system metrics, for example, the CPU utilization, and the other data such as the framework-specific and application-specific metrics, and the target metrics. Then all the metrics are sent to the A-tune. A-tune can make intelligent decision-making and then output the optimal lobs, such as the system lobs, framework-specific lobs, and application-specific lobs. These optimized lobs can make the performance of the system better. Now, we will give the architecture of A-tune. A-tune aims to analyze the resource usage, such as the computing, storage, and network of application workloads, support parameter tuning for mainstream applications in the industry, and improve tuning efficiency. The architecture of A-tune includes three parts. The first part is the intelligent decision-making, which includes online static tuning and offline dynamic tuning. And the second part is the system characterization, which includes the data platform, feature engineering, training, and inference. The last one is the system interaction, which includes the system full stack monitoring and the configuration service. Now I will give the two parts of the include the online static tuning and the offline dynamic tuning. Now I will give the detailed instruction about the online static tuning. The scenario of online static tuning is the common users and applications that need to be online at all times. The idea is that A-tune detects the current application workload, matches it to the lower workload based on the classification model, and then outputs the empirical parameters. The online static tuning have several key technologies. The first one is the important feature analysis. A-tune can automatically select important features to characterize applications accurately, and it can have two-layer classification, which can accurately identify the current workload. And the third one is the workload change detection. It can automatically identify the application workload changes and implements adaptive optimization. The second one is the offline dynamic tuning. The offline dynamic tuning is for advanced users who have high performance requirements. The idea is that the offline dynamic tuning includes three parts: include target device, tuner, and workloads. The idea is that the tuner sets parameters for the target device, obtains the feedback performance indicators, and iterates continuously to obtain the optimal parameters. Therefore, the offline dynamic tuning also includes 3 key technologies. The first one is the important parameter selection. It can automatically select important parameters to reduce search space and improve training efficiency. The second one is optimization algorithm construction. It can allow users to select the optimal algorithm based on application scenarios, parameters types, and performance requirements. The third one is knowledge-based construction. We can add the current workload characteristics and the optimal parameter to the knowledge base to improve subsequent tuning efficiency. Now I will give the A-Tune implementation framework. The framework includes 3 parts about A-Tune server, A-Tune client, and A-Tune engine. The A-Tune server includes data collection tool and system configuration engineering. The A-Tune server must be installed on a target device. The A-Tune client is used to interact with user and output the results. The A-Tune engine includes all the algorithms of A-Tune, such as the classification models, k-parameter selection models, model training, and the automatic parameter tuning. The 3 parts can be installed on different machines, and they can communicate through the gRPC. Now we will give several tuning results. For example, in Spark, there are several tunable parameters. If we use the default value, they can't get the best performance. Then we want to use A-Tune to select the best values for the given workload. For example, after A-Tune tuning, the performance is improved by 30% over the default system configuration and 5% over the configuration optimized by professional engineers. The tuning efficiency is 5 times that of manual tuning. Now, there are also several other tuning results. For example, we optimize the etcd system with A-Tune, increasing performance by more than 10%. The results were displayed in the OpenAULA application porting competition. And we also optimize MyCircle. MyCircle is optimized in 6 different scenarios on OpenAULA, and that operates with virtual machines with 4 cores and 60 GB memory, as well as 32 cores and 64 GB memory. In the OLTP insert scenario, the throughput is improved by 5 times. In the future, A-Tune will break performance bottlenecks. There are 2 kinds of improvement. For example, we want to from offline to online. There are several trends. For example, continuous performance tuning capabilities for online application to deliver performance as a service. For example, there are also several systems. For example, A-Tune provides online parameter tuning for cloud databases, and the Graduate focus on resource queue tuning for online applications. However, there are also 3 challenges. For example, the first challenge is the cold start. How do we deliver optimal performance in the absence of history data when a new application goes on? The second challenge is the adaptability. How can the cost of online training be reduced when a model is trained against online applications load that changes dynamically? The third one is security. How do we keep the performance of the intermediate tuning results above the preset threshold to ensure high system availability during tuning. The second one is from user mode to kernel mode. There are also several trends. For example, utilizing AI technologies to shift from conventional system configuration optimization to system design optimization. There are also several papers. For example, LinOS uses AI to reconstruct the kernel block layer and predict I/O latency, boosting SSD area performance. KML is another paper which builds an AI model in the kernel space to implement load-aware data prefetching policies. However, there are also three challenges. The first challenge is the computing overhead. How can model complexity and performance be balanced with the limited computing resources available in the kernel space? The second challenge is the timeliness. How do we infer and execute the highly dynamic optimization policies in milliseconds? The second one is the universality. How do we construct a universal framework for different optimization types that involve data collection and optimization algorithms for various kernel modules? Here is the ATune repository. Everyone can get the code of ATune. Please feel free to contact me if you have any questions. This is my email. Thank you.